Exam 1 overview. So as we just talked about, we'll have to maybe look over them a little bit, but I wanted to go through the exam real quick just so I can highlight some common mistakes that I saw and to demonstrate that the exam maybe necessarily wasn't as mean as it may have seemed on test day. All right, question 1. This question here, it says a quantity of water, 1 kilogram, just to make the math easy, is at 5 degrees C and it's heated using a 1 kilowatt electric heater in a constant pressure container. That pressure is 5 kilopascals. You can assume that the saturated liquid properties are the same as the properties of the subcooled liquid, because I didn't give you a subcooled liquid chart, so we had to assume that the enthalpy change associated with going from 75 kilopascals to whatever the saturation pressure is of the water was negligible, which is probably a pretty decent assumption. And then we want to know how long does it take to start boiling, so basically going from a subcooled liquid to a saturated liquid. And then how much longer does it take to start the boiling process to completely boil away all of the water. So we'll start off with our energy balance. Now, number one biggest mistake that I saw in this problem is people saying that the work was 0. The work is not 0. Because the work is volume expansion work. This is a constant pressure container. So when the system expands, it's pushing back the atmosphere, which requires work. So in this case, we move the PV expansion work to the left-hand side of the equation. Now, if we take this expression d dt and we distribute it, we have du dt, and then we have p dv dt. Now, we don't have to do the chain rule, product rule on this one, because we know pressure is constant in this apparatus, right? So these expressions are equivalent, right? Moving this over to the other side over here, which is the same thing as writing and we had an example, this is a P, and we've had a couple of examples on the homework illustrating that for a closed system at constant pressure, enthalpy is the term we want to use. Closed system, this goes to 0. So then ultimately what we're left with is Q dot, the rate of heat transfer, is equal to the change in enthalpy. So now we integrate both of these from state 1 to state 2. And then what we get is that delta H is equal to Q dot delta T. Where if we integrate this expression here, this right here, what we're looking at is integral of Q dot dt. The rate of heat transfer is constant. That's the full long form solution if we wanted to look at it that way. Consequently, if you say that the work is 0, then this would be delta U, and that's where a lot of mistakes were made. But ultimately the answers were, what were the answers? So we actually just had to look these values up. So enthalpy of state 1 was a saturated liquid at 5 degrees Celsius. Enthalpy state 2 for part A was a saturated liquid at 75 kilopascals. Right, we're not boiling at the normal boiling point, we're boiling it a little bit lower. And then for part, so this is A and this is B, and 3 was a saturated vapor at 75 kilopascals. So the step between here was the delta H of vaporization at 75 kilopascals and whatever the saturation pressure or saturation temperature was under those conditions. So the answers were for A was 363 seconds. And in fact, if you used delta U instead of delta H, it was almost the same because the enthalpy of a liquid is almost exactly the same as the internal energy of a liquid. There's hardly any PV expansion work that goes on. And for B, it was 38 minutes. 35 is what you got if we did the delta U, and that's because, again, gases do feel that PV expansion quite readily. Questions? Number 2, I'm going to go over how I meant it to be written, not how it was actually written, so this is going to be a little bit of a disparity. But I anticipate that I will regrade it having both of the two approaches being valid. So we have a refrigeration cycle. We have a pH diagram where we have a two-phase boundary. Let's see, what else do we have? pH, we have temperature lines that go across like this. And we have entropy lines that, how do the entropy lines go? They're kind of like this. And then we have temperature, like so. All right. So we have a starting condition. Let me draw out the refrigeration cycle. So we have a compressor, an evaporator, an expansion valve, and a condenser. So this is dP is 0, constant pressure. ds is 0, and this one is dH is 0. And our numbers are 1, 2, 3, 4. So our starting condition is a stream 3, the inlet to the compressor is a saturated vapor at -10. So if we say this is -10 here, that means our starting point is right here at position 3. Now we have to work backwards, going left and right. So going from 3 to 2, it's somewhere along a constant pressure line. This is across the phase boundary, so the temperature is constant and the pressure is constant. Now I meant for it to be right here at 9% vapor, but I mistakenly said it was at 9% liquid, which was here. So that is the mistake that I introduced into the grading. So I will go back and give credit for probably either of the two approaches. Not too hard to resolve. Now moving forward, going from step 3 to 4, this is isentropic, which means we are following along a line of constant entropy. So what we're doing here is we're going to be somewhere along this dashed line here at constant entropy, because this is an isenthalpic compression, but we don't exactly know where to stop. So we have to then look at step, let's see, 2 and 1 we have to work back out. So going from 2 to 1, right, going from after to before the isenthalpic expansion, that means this one here is a vertical line. So point 1 is somewhere over here. Point 4 is somewhere over here. And the last piece of information that we need to piece these two parts together is that the condenser is operating at a pressure of 8 megapascals. So if we have a line up here of 8 megapascals, that means we have to fall here, and then we have to fall there, and we have our refrigeration cycle. Or a shorter, more scrunched up refrigeration cycle. Makes sense. Question 1 is just a matter of reading off the difference between these two lines, or the difference between these two lines up here. Coefficient of performance. This is the heat in divided by the work out. So that would be, this here is QH. This one is the work in. So I'm just going to skip the energy balances. So effectively the coefficient of performance is equal to Q heat in divided by the work. So the heat into the system is H3 minus H2. The work is H4 minus H3. In a matter of just looking up the values and plugging it in. Questions apart from the mistake? Then the last part was, let's say, for example, we have a non-ideal compressor and it's creating entropy in the process. That'll cause the entropy to increase, which means that we're going to be somewhere over here. This gives us our delta S for the process. ds dt is going to be equal to 0 for an entropy balance on the compressor because this is a steady state process. So this is going to be equal to the mass flow rate, entropy of stream 3 minus entropy of stream 4, in minus out. So the difference between the entropy here and there is the rate of entropy generation times the flow rate. Questions? Okay, so I will have to collect these in a moment. Question 3. Question 3 says that ammonia, which is NH3, is a van der Waals fluid. This should all seem intimately familiar based on the homework that we had been working on. So in this one here, it asks for what is the work required to compress a cubic meter of ammonia from 1 cubic meter to 0.98 cubic meters. So let's start off with our energy balance here. It's a closed system, so I'm going to truncate that aspect there. Okay. What can we cross out on this equation?
Q.
No. This is an isothermal compression. Right? So I can calculate delta U with the van der Waals equation, because that's what we already did for the homework. Q, I don't know what the Q is. Work, I have another way to calculate the work though.
Yeah.
So instead of having to calculate the big, long, complex delta U expression that we had in class, it was just a matter of integrating the van der Waals equation of state with respect to volume and then plugging in the two specific volumes. So specific volume 1 was provided. It was 5 times 10 to the minus 5 cubic meters per mole. Volume 2, if you did the math out, is effectively just 98% of V1. And you had to calculate, I don't know if you had to calculate the number of moles. I did. No, you do have to calculate it in the final step. The number of moles, N, for the system was a big number. 19, almost 20,000 moles of ammonia in a cubic meter, which seems like a lot, but that's what the math says. So all we had to do in this case was integrate the van der Waals equation of state, RTV minus B minus 1 over V squared dV. Now, I knew that many of you would attempt to go the delta U approach to solve this problem. So I very explicitly said, this integral may be useful. The 1 over x minus d dx is equal to. I very explicitly provided that integral to kind of nudge everyone in the direction, because I don't think you had to use it if you did the delta U approach. Right, because in the delta U approach, you only end up getting the A over V squared, which you integrate to get minus A over V, right? So I gave that as an attempt at a hint, which did not go over very well. So then once you solve this step here, this gives us the work per mole, and then you just had to times it by the number of moles in the system, and I gave the number. So the final answer, I'll post the solutions too, but the final answer I got was 94.3 kilojoules after integrating. And the integration here is not too bad. Right, this is the natural log of V minus B over V minus B, and this one here is just 1 over V2 minus 1 over V1. So the integral was not difficult at all. Questions? We're doing okay? All right, question 4. Question 4 was a strictly plug and chug problem. Very little thought process needed to go into it. There were 2 strategies you could have taken. One was a bit easier than the other. So in question 4, I'm asking for the fugacity of a Clausius equation of state fluid. In this case, the pressure is RT V minus B, so it's the ideal gas law, but including the excluded volume term. The approach that I took was to integrate this expression here right, this is the more straightforward of the fugacity definitions. We didn't typically use this one because infrequently were we able to get our real fluid behavior in a volume explicit term. So a majority of folks use the ln of z minus 1 plus integral of, I don't remember off the top of my head, what is this? I think it's RT over V minus P dV. I might have plus or minuses messed up here a little bit here and there. But you could do this one too. It just involved calculating z. And then you could just directly integrate this same thing as you would have otherwise. But in this case here, I just rearranged this and solved for v, which was equal to RT over P plus B, I believe. And so then the integration was pretty straightforward. It was just basically involving the P, let's see, so the final answer for the fugacity that I got working through the mathematics. Listen, because this, let's see, this cancels with that and that, so all we're left with is B. So this ends up being B delta P, which is B P minus 0, which is just B P. Then including the RT, take the exponent, and that's how we get the final answer. So the correct answer was 14.7 megapascals. Okay, questions? And the last one, most people did quite well. I'm not exactly sure if it was just because people just drew a line and drew another line and then had an intersection and said, that seems like a good enough answer, which I suspect is the majority of it because a lot of people didn't put any work down. So we were generous this time, but I would not necessarily count on it in the future. So question 5 is we're mixing sulfuric acid and water, and we're trying to figure out what's the final temperature if we pull away a little bit of material in the system. So again, du dt. Now I modeled this as a closed system. Now how we can do this as a closed system is to envision a closed system with a barrier, and then you just remove the barrier. Right, so I'm doing the energy balance over the lasso of the whole system. But this is again constant pressure, so we have this pressure volume term right here. So ultimately our energy balance reduces to this expression. So if we integrate these processes here, right, the delta H of the process, change in enthalpy of the process is equal to the Q. Now, if this is adiabatic, that means there's no delta H change. And that's exactly what we had in the practice exam problem. So if we look at the table or the chart, this is the enthalpy. So this is 100%. Let's see, this is a weight percentage of. So this is water, and this is 100% acid. The reference condition is 0, and then we have a series of lines that kind of look like this. So if we did this adiabatically, we would mix to a point right here, which is about 40% acid, which is what the problem is saying. We could basically just read off the temperature was, and it's some pretty high number. But instead, we said that the Q was minus 150 kilojoules. So we're physically pulling away 150 kilojoules. So I was a little bit too nice on this problem. I should have made it so that it wasn't 1 kilogram of total mixture. If I made it so it was 4.8 kilograms of the total mixture, then you would have to actually be looking up how does that affect the change in the molar enthalpy, right? So in this case here, since all the math worked out quite nicely, right, the mass times the specific enthalpy change is equal to the Q out. So in this case here, we know that the final enthalpy of the system was minus 150 kilojoules per mole. So then it was simply a matter of drawing a line there and drawing a line there, and the answer met at 37.8. No one went through this amount of effort. So I should have definitely made this problem significantly trickier, where you actually had to consider, the mass change. Otherwise, people wouldn't have been able just to, fiddle their way through that particular question. So I was generous. In the future, I don't know if I should have been generous, but that was the decision that I made at the time. I guess I was in a good mood. Questions about the exam? So, please pass them in so that I can appropriately grade them.
Just to clarify,
Yes.
remove any points whenever you get grade right.
I can make no promises, but I'm assuming that if you got the points, it's because you solved the question that I intended to ask. But I will, unlikely that I will remove points, because that seems a little mean. So you can hold on to your exam if you'd like, but if you would like me to grade the question how it was written.
Well, in that case, can you?
Yes, you're right. Is this all? Okay. Now on to some lighter fare. So I don't want to exhaust everyone. I don't think any hardcore content is really going to be sinking in today, seeing as it's the last day before fall break and you just finished I'm assuming is a relatively aggressive exam from fluid mechanics. So instead, what I'd like to talk about is the question that I asked everyone on Wednesday. How can we get positive excess entropy? So a few folks have mentioned something that was on the right track. So keep the secret to yourselves, but I want everyone else to kind of brainstorm a little bit more. Right? So let's recap a little bit, remind ourselves of the question itself. Oh, and one other note. On the exam, and this is going to be true for future exams as well, I am not typically going to ask you an absolutely brutally aggressive derivation, right? Unless it's pretty explicitly clear, I just want you to plug and chug and demonstrate you know how to do the calculation, right? If I want to give you a brutal calculation that just makes you go through tedious calculus, I will just say, evaluate this derivative for this function, right? But in terms of actually testing concepts, if I give you a question where you're forced to go through a litany of mathematics and tedious calculations, I mean, when it gets to stat mech, that's actually kind of something I will test on. But for this classical thermo, if I give you a brutal question like that, then I don't have the opportunity in time to ask you on a bunch of other topics. So typically, I will try and ask questions that can be readily solved with only a few lines of math. And I think that was pretty appropriate and true for this particular exam after going over the notes. But for statistical mechanics, even when you have an equation, the units are oftentimes unfamiliar to us when we're talking about Planck's constant and Boltzmann's constant. Sometimes it's not explicitly clear if we're talking about a quantity per mole or a quantity per particle. And so oftentimes when you're doing statistical mechanics calculations, you'll be wildly off by 50 orders of magnitude just because you should have divided by Avogadro's number instead of timesing by Avogadro's number, right? 10 to the 23 off twice, right? That's an error of 10 to the 46. So with stat mech, there is merit to me having you evaluate a relatively simple expression because it's not as simple as it seems. Like you have an equation, it is explicit, but it's a difficult field. And it's non-intuitive units. Okay, but that's just kind of my general blanket statement for quizzes and future exams moving forward. Right, so what we talked about is if we have a system here, where in this case we are looking at the excess entropy mixing a component and as a function of, let's say, x of a. So we have an A-B mixture. Now, there is no excess entropy or any excess property of a pure fluid, right? Because there's no way that a pure fluid can behave any differently than how the pure fluid wants to behave. Now, the excess function is simply the difference between the real delta change of a property when you mix it minus how that mixture would behave if it were an ideal mixture. So we know that when I mix two fluids together, the entropy is always going to increase. And it's going to increase at a rate that can never be overcome by any other repulsive interaction between different particles. So entropy always, always, always increases. The function to evaluate that is xi times natural log of xi, which is a very trivial function to evaluate on a calculator. The downside is it has a discontinuity as you approach either pure component 1 or pure component 2. And the slope of which is also a discontinuity, right? Because it shoots up to positive infinity or negative infinity, depending on which derivative you're looking at. So to avoid this problem, all of that information is contained within the ideal mixture characteristics. So when it comes to tabulating thermodynamic data of mixtures, of which there are an infinite number of mixtures, right? I could take any compound A and any compound B and mix them together in any configuration. So to simplify the amount of effort that it takes to categorize all that information, we focus in on excess properties. Now what we talked about were two scenarios. One, where the excess entropy is less than 0, which has sort of an intuitive sense. And another, where the excess entropy is greater than 0. Now for less than 0, what we're effectively saying here is that they don't fully mix. So if I mix A and B together, let's say it's water and ethanol or water and isopropanol, the organic compound will associate with the organic compound and the water will associate with the water. Not fully, not completely, right? You still do gain entropy in the process. In this case, you're just gaining a little bit less entropy than you would have expected if it was a totally random ideal mixture like an ideal gas. Positive excess entropy. What does this mean? I've got a demonstration or a calculation that demonstrates why this is a realistic thing to actually happen. So, ideas. I'm sure everyone committed a lot of effort to thinking about this. So, we don't have to approach it right now. But what I'm going to do is I'm going to estimate the number of people in this room such that the density of people is equal to the density of a gas and the density of a liquid. Make sense? So if every one of you were atoms, for example, and this box size, we're not on the length scale of meters, but we're on the length scale of nanometers or angstroms. What I want to do is I would like to get a number from everyone. So gas, liquid. So shout out some numbers, I'll write them down. How many people do you think would be in this room if we had the same density as an ideal gas at 25 degrees C and 1 atmosphere? So how I did these calculations is I assumed that the same dead volume was present. So I used a cubic equation of state, the Peng-Robinson equation of state, to estimate the excluded volume. And with that information, I sort of kept that excluded volume constant across people. So I had calculated the excluded volume of a person. Okay, gas, how many?
0.
You have a 0.
1.
1. 2. They say what? 25. Okay, so we're getting some people who are actually playing the game. All right, we got a range here. Liquid. If we were liquid molecules, how many people would be in here?
1.
No, we're not 1. I'll put the 1, but say we say 50,
I saw them.
100. We got 1,000. Anyone else feeling adventurous?
Million.
What's that? All right, somebody's not very good at Price is Right. $1. Okay. So let's go through the calculation how I actually performed this. This is a late night calculation, so we'll see. I figured you guys would want something a little bit less intensive. So I've already explained the goal. So the Peng-Robinson equation of state is what I used. So Peng-Robinson equation of state to estimate the specific volume of water. So I guess I should have looked up the real density of water. It would be better. But anyway, I used the Peng-Robinson equation of state to do all of this. So the excluded volume of water, according to the Peng-Robinson equation of state, is 1.898 times 10 to the minus 5 meters cubed per mole. Now the specific volume of the saturated liquid was 2.21 times 10 to the minus 2 liters per mole, which is equal to 2.21 times 10 to the minus 5 cubic meters per mole. Well, that's not a particularly useful variable for me to think about when I translate from people to molecules. Now, the saturated vapor was a very low density, right? It was, because it's a saturated vapor, meaning that it's at a lower pressure than what we're at in this room. So you'd expect to have a significantly lower number of particles. So this ended up being 0.9215 cubic meters per mole. But this pressure here was low. It was 2.68 kilopascals. Now the Peng-Robinson wasn't too bad with water, but it probably got the water density a little bit, but I think it's still a valid order of magnitude estimate. So I calculated Z, the compressibility factor for water under these conditions. It was 0.9968. So that's pretty close to an ideal fluid behavior. So instead, I calculated the specific volume of an ideal gas at 25 degrees C and 1 atmosphere pressure, because that's a more interesting number, I think. And that one was 2.45 times 10 to the minus 2 cubic meters per mole. So you can see it's quite a bit different. But if you take the ratio of the pressures, they work out to be about the same, because the water's behaving pretty much like an ideal gas. So what I calculated was the percent of free volume. Right, that's the percentage of volume that the molecules have to move around freely. So what I did is I took the specific volume of the system, right? This is how many cubic meters per mole is that material is occupying. So from there I can basically draw a box, and that's the volume that I'm calculating. So if I keep the number of moles constant, right, the amount of space that is excluded by the particles themselves. The difference between those two tells me how much of that space is open around for the molecules to move around in. Does that make sense? And then for comparison's sake, I normalized it by the initial starting volume. So this tells us, and then if I times it by 100, that gives me the percentage of that system that the molecules have to freely move around in. Do we agree with this approach? This is just totally made up by me, by the way. So for our systems here, we have three systems. 1, 2, 3. We have calculations for percentage of free. So let's start off down here with this, saturated vapor at 2 kilopascals. It is 99.998% free volume, meaning only 0.002% of the room is occupied by people or molecules if I have this. But this is low pressure. Now for the ideal gas is 99.92. Which makes sense, about 100 times as concentrated. Or 50 times or so. For the liquid, how much of a liquid do you think is free for the particles to move around in? 14.1%. So we're getting close in a liquid to making that particles overlap. Now this is a continuum approximation of real molecule properties. In reality, there is no well-defined boundary of what is or isn't the edge of a molecule. Right? Electrons can spread out as far as they want to. You just have a reduced probability. So this is not an appropriate one-to-one analogy to a real quantum mechanical system. All right, that's the molecule side. So now we are going to keep the percentage of free volume constant across an atomic system versus our people in a room system. First step is, what is the excluded volume of a human? So B of a human, all right, is a question mark. So how I approximated this is I tried to calculate how many cubic meters is a 170-pound individual. So 2.2 pounds is 1 kilogram. I use the density of water, so 1 kilogram is 1 liter, and 1,000 liters is 1 cubic meter. So this is the volume of a person in terms of cubic meters, assuming that you all have the density of water and the weight of 170 pounds. 7.73 times 10 to the minus 2. So you're about 10% of a cubic meter. If that makes you feel any better. Makes me feel small, I guess. All right, so we're going to keep the free volume constant now. So the number of people in the room is the volume of the room times by 100 minus the percent free divided by 100 over the excluded volume of a human. So this top, the numerator, is the total volume occupied. And this is the volume of one person. All right, so we have the volume of the room, 100 minus the percent free volume, that's the volume occupied. I divide it by 100 to make that a fraction. So when I times the volume by the fraction of the room filled with people, assuming the same constant percent free volume, then I normalize it here. This is cubic meters occupied by people. This is cubic meters per person, so that flips up into from the numerator to the denominator. Denominator to the numerator, and that gives us units of people. So, I didn't actually bother with this one here because it's going to be a small number. Close to 0, I think. So it'll be 1/50th of the other one. So if the suspense is killing everyone. So I estimated this room, and I don't know if this is an appropriate estimate. I think it might actually be lowballing it a little bit. I said the volume of the room was 2 by 10 by 10 meters. Looks like it's definitely closer to 3 meters tall. And 10 by 10 is reasonable, I would say. What do you guys think? About 10 meters by 10 meters? So then if this is actually 3 meters tall, all of these numbers should be half again as large. Okay? So I'll do the math a little bit in my head to make it actually appropriate. So I'm going to change this on the fly to 3 by 10 by 10, which does seem like a large number, 300 cubic meters, but I mean, it's a pretty big room. I'm not counting the excluded volume of the ducting or the lights or anything. So if we are an ideal gas, so who's confident? Let's vote. Okay, we all have another chance to vote here. Okay, how many people say there's 0? Okay, how many people say there's 1? I'm going to keep doing this until I get people to actually vote. 2. We have 3 votes for 2. 25. 5 votes for 25. And for those of you who didn't vote, shout out, what's your vote?
0.
0? Who else? That doesn't add up, right? Oh, you got a bunch of poor sports too. Okay. It is 3. If we are an ideal gas, there would be 3 of us in this room. And we would be zipping around at like, I don't know what the appropriate speed is, but probably thousands of miles an hour. Right, and that's why we can have a macroscopic pressure working out pretty well, right? Because 3 people in here, but you're zipping around at hundreds or thousands of miles an hour. And it's a pretty small room, so you're hitting the wall very frequently. Hitting the room, I don't know, several times a second. Probably hundreds or thousands of times a second. Liquid. Voting time. I'm going to skip the 1. I'm going to skip the 5. Let's focus on these ones here. 100, 1,000, or 1,000,000. So how many vote for 100? Yeah, no votes for 100. How about 1,000? 1, 2, 3, 4, 5. I'll just say everyone. Anyone saying 1,000,000? Anyone saying 1,000,000? Okay. The answer is 3,330 people inside of this room right now. That gives us only 14% free volume. So, I have a question for everyone. How on earth do we squeeze 3,000 people into this room?
Very efficiently.
Stacking multiple layers.
Extremely efficiently. So liquid molecules do not have the luxury of being able to just willy-nilly float around. Liquid molecules have to be structured, organized, and meticulously oriented into positions to pack them in as densely as would be necessary to create a stable fluid phase. Anything in between the density of a liquid and the density of a gas is an unstable fluid. We know that because the cubic equation of state is a pretty appropriate way of actually estimating that. So if we take a look at our cubic equation of state again, right? This is unstable fluid. So if I'm starting off here as a vapor and I'm getting pressurized, I can interact in this area over here a little bit, right? I can be a little bit subcooled and still be a stable fluid. Likewise, if I'm a liquid, I can be superheated a little bit and still be a stable fluid. But there is a region in between here that, according to the second law of thermodynamics, says you cannot be in this region because it doesn't behave as the universe would be if it were a stable system. So now, with this new insight, let's talk about positive excess entropy. Entropy is a representation of disorder. Now we know that kind of from a statistical mechanics approach. Now technically we haven't covered that in a class, but we all have that sort of background from a physical chemistry perspective, and it's used oftentimes to describe phenomena at an undergraduate level in a thermodynamics class. Back in the 1800s, we didn't have that information, right? We didn't even have the information of what temperature was. So atomic theory and statistical mechanics, which were founded by Boltzmann, among others, gave us that insight that we could describe all real macroscopic processes assuming that atoms were the driving force and cause of all of this. So, molecules see randomness differently than we see randomness. So, if I were to take 3,000 people and somehow convince them to pack into this room, I would have to do so in a very meticulous and organized manner. Otherwise, I could not get 3,000 people to stack into that room. Now, if I just said 3,000 people, give them a bunch of caffeine and have them run into here, there's no way I could ever get 3,000 people in there. So totally random mixing, where one person's orientation is 100% uncorrelated from someone else's orientation. That's the assumption of the ideal gas law, is never going to get all the people inside of this room. So what positive excess entropy represents means you get an increase of local order in order for you to have a greater extent of disorder in some other dimension. So now for people, that might involve making a liquid crystal, right? So if we stack everyone up from floor to ceiling, right, you maybe have some wiggle room to go forward and backwards, right? That is a way to generate entropy in the system. But if everyone is trying to twist and turn or has their arms out spinning around, there's no way you could ever get that many people in the room. So when you have a positive excess entropy, it is actually a coherent structural organization of a portion of the fluid, such that the remainder of the fluid, or there is a movement or a degree of freedom mode that is accessible for the molecule itself. But if everything is just spinning around like a top, right? If everyone has their arms out spinning around, those arms are going to bind up and you're going to jam and you're going to get stuck and gelled in a particular configuration. But if everyone is ordered like soldiers to go stack very organized, then you may be able to jump up and down or spin around in a circle, right? So if my arms are in, then I can spin around in a circle without, hitting another molecule. So that's how a molecular system behaves, which is distinct from our perspective, what we view randomness as, right? So molecule randomness may look very ordered from our perspective. And one of the key things is, can you control that degree of ordering so that the molecules think it's disordered, but we get them to organize in the right way, which is a cool kind of pathway for material synthesis and design. Okay. So hopefully that wasn't too heavy for just before we depart for fall break. But yeah, I was a little surprised by the answer itself. 3,000 people. Seems like a lot of people in this room. So get your friends, see if we can do directly. Okay. All right, have a good fall break. See you later. I will post the homework at some point.